This is Lecture 1 from Module 1 in the book Problem-Solving Guide for Electromagnetism and Optics, 3rd edition, Introduction to the Concept of Electric Charge. Atoms are composed of protons, neutrons, and electrons, atoms like carbon, zinc, oxygen, nitrogen. The protons are positively charged, the neutrons are neutral, the electrons have a negative charge. The standard unit of electric charge is the coulomb. The charges on the particles that comprise the atom are the proton plus 1.6 times 10 to the minus 19th coulombs. The neutron is neutral, has a charge of 0. The electron minus 1.6 times 10 to the minus 19th coulomb. So the electronic charge is a small fraction of a coulomb, 10 to the minus 19th. That is a lot of zeros. To wrap our heads around the concept of charge, let's consider a penny. There's a penny. Penny's made of zinc, primarily, has a mass of 2.5 grams. Let's calculate the total charge of all the electrons in a penny. Zinc has an atomic number of 30, so 30 protons, 30 electrons, an atomic weight of 65. We can calculate how many atoms are in 2.5 grams of zinc. The answer is 2.3 times 10 to the 22nd. Each atom has 30 electrons, so a penny has about 7 bazillion electrons. 7 times 10 to the 23rd electrons. Each electron has a charge of 1.6 times 10 to the minus 19th coulombs, so the electrons on a penny have a charge of minus 110,000 coulombs. Pennies are neutral, so protons, if you add up the charge on all the protons, you get plus 110,000 coulombs. So let's consider two pennies 1 meter apart in deep space. There they are. They are attracted to each other by their gravitational force. They have mass. They pull on each other. We can calculate the time it would take for them to collide, and it's long, more than a month. Those pennies will not zip toward each other and crash into each other. Very slow. The gravitational force between two pennies 1 meter apart is very small. It's like 10 to the minus 16th newtons. Now let's imagine taking 1/1,000,000th of the electrons from one penny and transferring it to the other penny. 1/1,000,000th of the total number of electrons on one penny. If we take them off, we'll leave that penny positive. The penny that we're putting the electrons on will be negative. They'll attract each other. Their charges are opposite. We can calculate the force between them. And it's big. It's 90 million newtons. Almost 10 to the 8th newtons versus 4 times 10 to the minus 16th newtons. Huge difference in forces. If you could do this and you let those pennies go, they will accelerate tremendously and smash into each other at a tremendous speed. A fraction of a second, they're going to collide, and they're going to collide at like 250,000 meters per second. You can't even do this. If you try to do this, the penny would start ripping. If you tried to suck the electrons off the penny, it's just going to suck electrons from the air molecules. Sparks will be flying. You just can't do it. I mean, that's a lot of charge. 110,000 coulombs is a lot of charge. A lightning bolt transfers about 100 coulombs of charge. So a lightning bolt transfers about 1/1000th of the total number of electrons on a penny. So the reason for this big disparity in forces is the value of the two constants in the equations. So the gravitational force equation is G, a constant, mass 1, mass 2 divided by r squared, and the electrical force equation looks very similar. It's a different constant, the electrical constant, times Q1, Q2 over r squared. So this is the gravitational force constant times the gravitational charge 1, gravitational charge 2. We call that gravitational charge the mass. And this is the electrical constant, that electrical charge 1, electrical charge 2, divided by the distance between them squared. Newton's gravitational constant G is 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. Coulomb's electrical constant is 8.99 times 10 to the positive 9th Newton meter squared per Coulomb squared. So that's a lot of orders of magnitude difference between those two force constants. There's some other differences worth noting. We've only found one type of mass. So any mass attracts other mass. It's always attractive. There are two types of charge. One type of mass, two types of charge. And we call them positive, negative. We could have called them up, down, left, right, blue, red, whatever. The rule is, unlike charges attract each other, and like charges repel each other. That's how the universe works. The magnitude of the force between two charges is this equation, and I've put absolute value signs around the Q's because all I care about is the magnitude of the force. I know which way the force is going because like charges repel, unlike charges attract. I don't need that equation to tell me the direction of the force. I can look at the signs of the charges and figure out the direction of the force. I use this equation to tell me how big the force is. And the force is proportional to the constant times the magnitude of the two charges divided by the distance between them squared. So let's see how this works. Let's do a problem. Figure out how charges exert forces on each other and how to calculate the net force. So here's the problem. Plus 2 nanocoulomb charge is fixed at the origin of a coordinate system. There's a minus 3 at the point 1 centimeter in the x, 2 centimeters in the y. We want to know the force on the plus 4 that's located at the point minus 2, plus 2. When problem solving, it's always a good idea to draw a good diagram, to think about what's going on before you start plugging numbers into equations. That should be the last thing you do. So here's our good diagram. There's the minus 2, there's the plus 2 nanocoulomb at the origin. And I like to put those as solid, black, because that reminds me that they're positive. This is a negative charge, and I made it a little bit bigger because it's bigger. It's minus 3 nanocoulombs. That's plus 2 nanocoulombs. These are the two fixed charges, and we want to measure the force on this charge, which is plus 4, which is at minus 2, plus 2. So it's very easy to make a mistake when putting the charges down, and of course if you make a mistake and put them in the wrong place in the coordinate system, all of your calculations are just exercise. Next thing we want to do is to draw the direction of the forces, qualitatively sketch the force direction. So the 2 is going to push on the 4 up that way. They repel. They're like charges. We can put that one in. This is negative. It's going to pull this guy. And it's bigger than the 2. It's a little bit farther away. It might have a bigger charge, bigger force, but it's going to pull it. So we put an arrow to the right. We're not too concerned about, we want to roughly get the length of those arrows right. But at this point, we're just drawing the direction. And with these two arrows, we know that the force should be up here somewhere, the net force. If this plus 4 nanocoulomb charge is released from this position, it should accelerate something like that, somewhere up that way. We can calculate the magnitude with this equation, kq1 q2 over r squared. We know the charges, all the charges are given. We have to get the distances. If we're going to calculate them, we need the distances. The distance between the plus 4 and the minus 3 is easy. That's just 3 centimeters. We have a diagonal distance here, and we can get that using the Pythagorean theorem. It's 2 over and 2 up, and the hypotenuse is right there. And we can calculate that distance, 2.828 centimeters, and now we are ready to go to get the lengths of these two force vectors. Between the 4 and the 3, that's a pulling force. There's the equation. There's the K. I'm not worried about the signs. I know the direction. I want to know how long it is. So I just put the magnitudes of the charges in there. The 3 on the 4, and the distance is 3 centimeters. Note I convert all of these to SI units. 3 nanocoulombs is 3 times 10 to the minus 9th coulombs. 4 nanocoulombs, 4 times 10 to the minus 9th coulombs. 3 centimeters is 0.03 meters. Now my units are going to work out to newtons. And I get the answer, 1.2 times 10 to the minus 4th newtons, and I put it on the force diagram. That vector has a length of 1.4 times 10 to the minus 4th newtons. Now we can get the other length. The 2 is pushing on the 4. I have 2 nanocoulombs, 4 nanocoulombs, and there's the distance in units of meters. Punching the buttons on a calculator gives me 8.99 times 10 to the minus 5th, and I want to put that on the diagram as well. Now I want to add these two forces to get the net force. And to do that, we break them up into x and y components. This guy is already, he's purely horizontal. I don't have to break him up. Force from the 2 nanocoulomb charge at the origin is up at 45 degrees, so I need to split this vector into x and y components. And I can do that with trigonometry. The force from the 2 Newton in the x direction, it's negative, it's backwards, 8.99 times 10 to the minus 5th times cosine 45. That gives me the horizontal component. To get the vertical component, it's positive, it's upwards, and I'm going to go sine 45. That's this side, the opposite side. Punching the numbers gives me, in the x direction, minus 6.36 times 10 to the minus 5th, and in the y direction, plus 6.36 times 10 to the minus 5th, so I can replace this vector with an upward vector and a vector to the left, like that. And I know their magnitudes. The net force in the horizontal direction is simply this force minus that force. This is 12 times 10 to the minus 5th, 6.36 times 10 to the minus 5th, which gives me 5.64 times 10 to the minus 5th, and it's to the right, it's positive. There's only one force in the vertical direction, so the net force in the vertical direction is simply 6.36 times 10 to the minus 5th newtons. So, what we've done is we had those two vectors, and now we have the x and the y component. And the reason why we did this is now we can use Pythagorean theorem to get the magnitude of the vector, and we can use arctangent to get the direction of the vector. So we have the horizontal and vertical components. The net force is f sub x squared plus f sub y squared square root, and we get 8.5 times 10 to the minus 5th newtons, something like that, in that direction. We have the net force. Now we have to get the direction, and I redrew the forces down here so we have a bigger diagram. There's the vertical force, there's the horizontal force, and we want to get this angle. That's the opposite side, that's the adjacent side. Tangent theta is 6.36 divided by 5.64. We can take the arctangent of both sides and get the angle. It's 48.4 degrees. So now we have the answer to the problem. The force on the plus 4 nanocoulomb charge is 8.5 times 10 to the minus 5th newtons at an angle of 48.4 degrees above the positive x-axis. So these two vectors combine to give that vector, 48.4 degrees above the positive x-axis. And that's the answer to the problem. Point charges and the forces they exert on each other.